All right. So we'll do everything now in the constrained world, whatever we did for the unconstrained setting. Constrained optimization. So what is the problem we want to solve? We want to solve minimize f of x. X belongs to. So x is going to be closed convex. If you want, you can also call it bounded, compact, whatever. Throw in whatever conditions you want. So whatever workhorse for optimization, what is the algorithm which we looked at? The main algorithm. We looked at several other algorithms, but what is the main algorithm for optimizing when there is no constraint on x? What was our main algorithm? Was essentially t is equal to t minus eta del for xt. Call it gradient descent, you call it steepest descent, whatever you want. It's only in particular norm it is steepest descent, but that's okay. So it's essentially the gradient descent algorithm. This worked as long as was equal to Rn. There is no constraint. Now, if I impose a constraint, what would you do? That's the first question you should ask yourself. This will take you wherever it can, and given that the constraint set is all of Rn, xt always belongs to Rn, which is equal to x. So things are okay. Now, given that the final outcome you want, or the final answer you want, should belong to this set, what would you do? If you want to solve or follow this particular method, there is no requirement that you should only follow this method, but if you were to do that, what would you do?
Follow this method until we reach one point of the boundary.
What's the guarantee? It reach the boundary. But in the gradient descent step, you're not conforming to any constraint on x, right? You're just going wherever the gradient takes you. It need not remain inside the constraint set x. So you might get an answer which is infeasible. What else can you do? Don't limit yourself. This is a simple thing, right? You're given, when x was unconstrained, you're given this algorithm. If you want to use this algorithm under constraint, what is the most obvious thing you would do? Scale.
Scaling the set x.
How can I scale the set x? Set x is x. This is producing iterates xt, xt plus 1 and so on. You want the final answer to belong to the feasible set.
Project xt.
Okay.
The closed sets.
Closed. What is closed?
X.
Chi or whatever. Okay, so what do you want to do with the algorithm?
Let it be again as it is, but then after getting xt up to a certain error or like up to a certain point where we can say that we are having the mean value of fx at that point, then we can project it back to.
So one projection.
Yes.
Okay. Okay, one alternative. Yes.
Or I don't know if it is right or wrong, but
there's no question of right or wrong.
But after like first getting the first widget, we can project it to Kai, then apply our algorithm to that point, to that projected point. Then we will get another point. If it is in Kai, then again we can apply, or if it is outside, then again keep on projecting.
Okay, that's another alternative. What else can you do? Do people follow what he said? He's just saying repeatedly, keep projecting back. So wherever your gradient descent takes you, let it take you wherever. And from that point, come back to the feasible set. And you keep doing this. We'll drop pictures. Don't worry. Do you see the difficulty with constraint set? Like, what is the difficulty? Why do you have to worry so much? The gradient itself is not zero. That much is the first thing you should notice. The gradient need not be zero at the optimal point within this feasible set. That's the first problem you should encounter. So there is no way of controlling that the gradient is small, I can do something. Okay, so let's try to draw these two. So let's say this is my guy. The first algorithm is said, number one, gradient descent till convergence, or let's call it unconstrained gradient descent till convergence, and then project. Number two is keep projecting after each step of gradient descent. So how will this look like? Same x. So suppose you start here, let's say your x0. Okay. You go in the direction of the gradient, or let's this is your, I'll tell you what y0 is, and then you project back to get your x1. And again, depending on where it goes, if it's y1, then it remains as it is because it's projection onto x is set. So y t is nothing but xt minus eta del f of xt. Okay, and xt plus 1 is equal to projection of yt comma. Right? That's your algorithm for this time. Keep going. What will this do? This will just run xt equal to xt minus 1 minus eta del f of xt. Whenever it stops at, let's say, x terminal, you go to projection of xt comma pi. These are the two different algorithms. Okay, which one should you think about, which is easier to analyze or whatever? Any comments on the quality of these two algorithms?
So in a constant set, it is not necessary to start with like any point.
What do you mean?
Like not within the set, you are starting from outside.
Not
The
necessarily.
initial point would not be necessary depending on the algorithms.
So that itself is a problem. If you not noticed so far, finding a feasible point itself is an optimization, convex optimization problem. Have you noticed that? So if I give you a set X and ask you, give me a feasible point, which should belong to that set X. What problem I have to solve? to get that. So there is no guarantee that somebody will give you a point to begin with which is feasible. It could be feasible and not feasible.
Why does one have to work at all?
Tell me, why should it work and why should it not work?
This is just finding the global minimum.
Yes.
And then it is directly projecting the global minimum. Why should that in any way imply that projects of the minimum?
I didn't claim anything, right? This is an algorithm. I didn't claim any guarantee of this algorithm. If you're trying to build an argument against it, tell me what is that argument. Remember, the functions are allowed to be convex. Like we're considering ourselves to now convex functions. Functions are convex. Think about it. It should be something should be bothering you on that algorithm, which you could have done with algorithm 2, but not with algorithm 1. Or everything is okay.
No, algorithm 1 is only, like, is that using of the set, the closed set, is only once, and
Sorry?
like the closed set X. So until the last step where you're getting the XT, we're not using anywhere the X
Yes.
constant of the.
But that's not an argument to say that's a bad algorithm. It should be I'm producing a feasible point. See, because if X star, the optimizer, unconstrained optimizer, lies in the interior of X, tell me what is that a bad algorithm?
In case of one, they already have presented on.
So you will produce an optimal solution up to whatever accuracy. It's not a bad algorithm as long as you can guarantee that the optimizer sits inside X. So all that problem you should get problematic is only when it's on the boundary. And that's why it's difficult to analyze. The algorithm 2 will turn out to be very easy to analyze. I don't have a counter example right now to say that that algorithm is actually bad. But the only difficulty lies when the optimizers end up on the boundary. For any constraint problem, for a constraint problem, you should know that the optimizer happens to be in the interior of the domain. There's nothing to do. You can just apply your own constraint algorithms. It will get there. The difficulty is only when you have a wall. Like let's optimizer sit on the boundary, and that's where you have a problem. That's where you have to worry about it. Okay, so now we're going to analyze algorithm 2. Keep thinking about algorithm 1 if you like. If you don't like, then tell me why you don't like.
Will algorithm 1 actually produce an optimum insight on the?
It will see definitely at the end. You're projecting it back somewhere here. It's a feasible point. Point is, if the optimizer is here, what is the distance essentially? That's what you have to worry about. That how far is it from the optimizer? If it's inside, then already this algorithm will make sure that it goes inside. That's not a problem. It's only on the boundary where you have to worry about things. That where the optimizer is and where the projection goes. That's all you have to worry about. Is the idea clear? What we are doing? This is repeated projection. Every time, every iterate I'm producing. So this additional advantage here is that I don't have to worry about when to terminate. Every single time I'm actually on the feasible side. Terminate whenever you want. And the guarantee will be given in terms of the number of iterations you run so far. Okay. So first we'll assume just the Lipschitz. We'll not assume smoothness. So theorem. Let F be convex and Lipschitz. with parameter L. Choose the step size eta to be diameter. I'll tell you what diameter is in a minute. Times L times square root B. So that's my step size. B is nothing but the diameter. So B is suprema over x comma y, the distance between. That's just the diameter of the feasible set. Then the projected gradient descent. So algorithm 2 is called projected gradient descent, PGD, satisfies f of the average of all the points seen until time t minus, so x star by definition belongs to the constraint set, is less than equal to d times L by square root. Yes, what was the question?
But if we are, our doubt was that if the optimizer lies in the boundary, there might be trouble. So if we, after getting the optimizer on the set X, if we work with the set X plus epsilon,
Okay.
then anyway the optimizer will be inside of the set X plus epsilon, which is also closed and.
Okay, but how will you describe such complicated sets? You have to close it also.
Like, if we just take the X, yeah.
You'll have to close it, right? It may not be closed.
Like,
You have to convexify it.
yeah.
So,
no, but we are given that the set X is convex also.
yes. But if I add whatever you're adding,
Yes.
that may not be convex. That itself could be a problematic thing, right? I agree what you're saying. In the abstract sense, yes, it's correct that I could just add small balls around,
Yes.
but that itself will present a difficulty. So technically, it's okay what you're doing. All right, so notice what is going on here. In t iterations, what I'm claiming, that if you take the average of the iterates, I'm not saying xt, this point is feasible. Is that okay for everybody? That this point is feasible? Each point is feasible. Projected gradient descent ensures that every point is feasible. So the average is feasible. The distance between the average and the optimum is falling down as 1 by square root t. Interestingly, it is free of dimension of important to note this. The answer really depends on the diameter. We'll see another algorithm which is more well known, like ellipsoid or center of gravity algorithms, which will end up depending on the dimension. Will give you a better bound on the error. All right. Okay. So how do I prove something like this? It is in fact elementary. We've done similar things for unconstrained case. So one simple lemma, or let's call it lemma. So this, my definition is nothing but That's the definition. You can remove the square also, it's okay. You can work with any norm you like. Right? That's my definition. So lemma is that if x belongs to chi and y belongs to Rn, then projection of x comma chi minus x transpose is projection of y comma chi minus y. Does everybody see why this is true? Make a picture. So what is that?
The R.
Sorry?
The R.
R?
Projection is the R.
Okay, R. Thank you. What is the picture? So think of this as chi. Y is some point outside, let's say. X belongs to chi. What are you saying?
Y belongs to Rn minus chi. It's like,
Not necessary, because otherwise this is 0. If I belongs here, then this quantity is simply 0. Okay. Sorry, it should be y. Should have jumped on top. This is also 0. So if y belongs to chi, there's nothing to prove. It's identically 0. So only when y is outside, I have to.
Okay.
Right. So now what is projection here? This is going to be the projection. So what is it saying? This quantity is nothing but this vector. What is this quantity? No, it's not distance. This quantity. This is y. This is projection of y on x. Right. What is this vector? This is the vector. This vector. What is this inequality sign? And why this better be true?
because chi is convex. Right?
Yes.
So then from there,
You've shown this multiple times. I know, but because I'm going to use it, so I'm going to write it again. But why should this be true? If anybody has a doubt, one line answer. Suppose it was false, let's say. What would go wrong?
then you would have that the angle between them will be perceived. Okay. And
All it's saying is obtuse. But why should it be obtuse?
yeah,
So if
Sorry?
we take a plane, support
Yes.
vector,
So the picture is like, should make it slightly lower. Things will be easier to think. Let's take y here. Now it should be easy to see why this should be true.
the projection is perpendicular to the hyperplane, that is,
Do we have to go there?
and I mean,
By definition, this is the shortest distance, right? Isn't that enough? This is this thing over here. So this is the vector, which is this one. So let's call this A. This is the vector A. This is vector B. Which is that? This guy is B. Suppose this was not true. If it was making an acute angle, what would go wrong?
Then there would be a point of the line.
It should be closer. And it would not be the projection. As simple as that. So this you've done so many times. So I'm just going to let you just absorb it for a second. Which you're going to use this essentially as our major tool. The proof is actually elementary, as I said. Okay, so what do I want to prove? That the average is not too far from the optimizer in terms of F. So let's look at where
so
X star by definition is this quantity. Okay, so let's start with what is happening to the SH step iterate. We'll take the average later because of F being convex. Jensen's will give us whatever we want. If we can control this minus Fx star, we will get what we want just by taking the average essentially. That's the basic point. Okay, so what can you bound this by on the SH? This is less than or equal to how much by convexity? F being convex will give us something. What is that something? Gradient of F of if I wanted XS, then what would you do? Yes. Okay. Now by definition, what is this quantity? Something I can say with this? I'm running an algorithm, right? What is that algorithm?
It is bounded by initiative.
So this is incorrect. What is this quantity? Sorry. What is this quantity? Remember, two iterations, right? Y and X. So Yt is xt minus eta del f of xt, and xt plus 1 is projection of Yt. That's the algorithm. What is this? This is nothing but eta times something here, xt minus Yt over eta. X, I want XS here. Okay. Now this is in some form of this type. People notice that this inequality, bias is not required to be feasible. Exactly like we didn't care about y being inside X. It could be anywhere. And what is the projection? XS is a projection. X star is also sitting inside X. So I can apply that inequality. What would I get? Sorry? Would that be sufficient? All I would get is f of xs minus f of x star to be less than. Something is wrong, right? That can't be true. Okay. Which one? This one.
Yeah.
Okay. So that inequality is anyway not true. Because what would you get? F of xs minus f of x star to be less than or equal to 0. That definitely is not true. So I can't apply it directly. But what can I do? Something before that? Something more elementary? Inequality. Yeah. A transpose B is equal to A square plus B square minus A minus B whole square. If I can apply at least this here, what would I get? What should be my A's and B's here? You should understand that some things are natural, you want to keep, and some things are you want to destroy. What are those things which you would like to get rid of? You would like to keep the distance xs minus x star as it is, because that's what you really care about. while somehow these things should disappear. And somewhere you have to also use the Lipschitz property so that you can bound the gradient. Okay, so this should be equal to 1 by 2 eta xs minus x star the whole square plus xs minus ys square minus ys minus x star square. Okay, that much is okay. Now, which terms should I keep and which terms I should try to get rid of?
The second one.
The second term I should try to get rid of. What is the second term? It is purely in terms of the gradient. Right? xt minus ys, so xs minus ys, according to my definition, is nothing but purely eta times some gradient, which because of Lipschitz net will be controlled. So that I can take care of. What about this one? So let's keep that as it is for the moment and we'll see what happens. So 1 by 2 eta, this term is xs minus x star the whole square minus ys minus x star the whole square. And this term I'm pulling out. So there will be a eta square here, which will get cancelled. So it will be simply 1 eta by 2 gradient f of xs.
We can use the variable the second term to get rid of
Sorry?
the previous lemma.
Yeah.
Somehow we want to use it on the second term, that ys minus
This term. Okay, we'll come to that. So now, okay, so this I can control because of the Lipschitz nets. This is at most L. I get essentially these two things. What would I like to happen?
This one thing. If you multiply the first that a square, the form of a square plus b square by a square itself.
Okay.
So in the second term, it will be like y minus ys minus x star norm times y x minus x star norm whole square, and that we can use that inequality here itself.
But just try to notice something about these two terms. Is one larger than the other? And keep looking at here. The distance being captured with respect to x star. One of them is a projection. So either it is 0 or something is larger. I'm talking about the difference. Both these quantities are comparing the distance with respect to x star. So there is some x star. Where does xs and ys lie? Or you can look at one step later also if you think. Think of distance of yt to x star and xt plus 1 to x star. Which one is shorter? Is everybody with that? So yt lies somewhere. Either the projection is identical, in which case the distance is the same, or yt is here, while xt plus 1 is here. So the distance from xt plus 1 to x star is smaller than distance from yt to x star. Can we use that somehow? Correctly, what is on the board are identical terms, because I don't have control. But look at the left hand side. It's for iterate number s. I also have to worry about s plus 1, s plus 2 and so on, because the guarantee I'm giving you is only in terms of the average. Right? So does something click?
We take the average of all,
Okay,
we get the
keep going.
That is comments will get projects the top format information.
That you can take later, right? That will be simply Jensen's inequality. But before that, what's the one thing you should notice? Something to notice on the board. I've got this relationship for every S. But the interesting connection I have with respect to X star is one step ahead between yt and xt plus 1. How do I exploit that?
Is a theoretical summation can see that.
Somewhat. What should I sum?
Is not
Just sum it over S from the left hand side and right hand side. Is that what you're suggesting? Don't hesitate. Okay. So what if I sum it? What will happen? This will give me summation S going from 1 through T. Is everybody feeling cold or just me? Feels cold? You know that, right? There is a control here. It's supposed to work. Huh? It's not always this cold. So that means it works. It'll take some time to get this. It should work. It's flashing right now. It go there. All right. So if I sum this, all of this, sorry, S going from 1 through T. What will happen here? Which terms will cancel out and which terms will remain using this property? So this is how I'm going to use this property. These are currently identical, so I can't do anything. But every time I get the next one, there is some interesting connection.
So x s will be cancelled out with x y is to be useful.
Okay. So what will remain? Just tell me that. So 1 by 2 eta
X s
by xs. Either if it's telescopic, the first and the last should survive. Which is the first term?
xt plus xt minus x star
Okay.
plus y1 minus x star.
Y1 or x1. Which one should survive?
Yeah, minus y is y1. Minus
Okay.
minus.
Mm-hmm.
No, there will be plus.
We'll fix in a minute. And this will come as it is.
A is in summation.
Sorry, square here. Okay.
Minus of a minus b. Minus of a minus b each time.
Okay. What's the consensus? Minus or plus?
Minus. You're right. Yes.
Okay. Suppose I get to here. Now what? Remember what I want to prove? That it falls as 1 by square root t. Is that good enough to prove 1 by square root t? Next, you should notice you have choice of eta with you to play with. You can choose whatever you want. Okay. You can make it eta t also if you like. We are not really played with that. All these are slightly delicate because when you're choosing eta to be 1 by square root t, you're already assuming that you're stopping at a particular time. So these are delicate issues. We'll push it to some other level of the course we'll teach sometime. But at the moment, what are we saying? When we choose eta equal to 1 by square root t, that means we already know when we're stopping.
So let's
And why can I do that? Because of the following guarantee. That if I want an error to be epsilon, I know exactly how much t I should take. So that's why I can do all this. Okay. So is this good enough?
So the other way is like keep continuing until it falls within the error.
But then you have to backtrack and fix your eta, right? Because here I'm taking a constant step size. I'm not changing the step size. There are algorithms which work with 1 by square root, the running constant. So then it becomes eta t. So eta 10 is equal to 1 by square root 10. And that still also works. This particular thing will not. In general, that also works. Here I'm assuming eta to be constant, but dependent on the time at which I'm stopping. Okay, is it good enough for my guarantee? Remember, I have choice of eta to make here, which I can choose whatever I want. Question is this good enough? There is a bound on this. What is the bound on this? Because of my Lipschitz condition.
It's on something like this for each and last one.
No. Gradient. When the functions are Lipschitz, what's the upper bound on the gradient? Not at most L.
Yeah.
This is at most L square, whatever the iterate is. So this is at most T times eta times L square. What about these terms? These are essentially R square plus R square.
What is that?
Sorry, diameter. What is this at most diameter? This is a minus. That's why I don't care. This is at most the diameter square. So this is at most going to be in the order b square by eta. I can forget about everything else, plus t times L square eta. This is how it is moving. So what is the obvious choice of eta to pick? See, you want to kill t first of all. So it better be that go by 1 by square root t. But that's not good enough because it's going to L square and b square. So you also pick b and L appropriately. So that's what the choice we picked here. D by L square root t. That will take care of this quantity. I have not shown this yet. All I have shown is the summation of all the errors up to time t. Let's write it again. So
even if it's convex, right?
yes, so that's where we'll eventually apply our Jensen's inequality. So summation f of xs minus fx star s square from 1 through t is at most how much? D square by 2 eta plus eta L square. Sorry?
E into L.
What?
Yeah. E into fx star.
Okay, so now what I do, how do I pass this to what I want? I want s 1 by t. That's what I want to have my final minus f of x star.
Just listen to it.
This is the guarantee I want finally. Let's say eta is how much? This much is square root t, correct? D over L or L over D? D over L. Yeah, D over L. How do I pass this guarantee to this one?
Yeah, it's convex. So
Mhm.
say that f of that average is the average of each of the points.
So 1 by t summation xs s going from 1 through t is less than equal to how much?
Average of the
1 by t summation xs. That's all. This is a constant. I don't have to touch this. And you get your answer. The proof is kind of elementary. Doesn't do much compared to the unconstrained case. Try to, like as an exercise, try to do something like this for your algorithm number 1 and see where you get stuck.
just one. If we can somehow guarantee that at some point any iterate false interior of the convex.
That doesn't mean it's globally optimal.
No, but yeah, I'm just saying that if it falls in the interior once, then there no need to be remain in the interior, right?
No.
When it falls.
Yeah, because the gradient descent is not respecting that. You first take gradient descent and then project. That's the algorithm you are following. There is no guarantee that once you are inside, you'll remain inside. So that's the difficulty with Every time you have to project.
Even if we have extra inside that, then also this is,
Then tell me what happens.
then the direction will be okay.
Not necessarily. Depends on the function. Okay. So now let's say we can do better if the functions are smooth. So what was our definition of beta smooth? When the gradients themselves are so Lipschitz. Okay. Anybody remember the guarantee when we did this for the unconstrained problem? If you have to look back, then it's okay. By the end of the course, this much at least. Which one?
Not only like the theorem whatever you have stated, not only involve beta, also the
It's much stronger, right? So the proof we did, we showed that in the unconstrained case, f of xt minus f of x star was less than equal to 2 times beta x1 minus x star, how far we are when we start, divided by t minus. This is what we do. Do you think we can get the same rate in the constrained world?
x1 will be the product.
Sorry? No, this was what we got in the unconstrained world.
But in the constraint world, where x1 will be basically you are taking the initial word y1.
So I could take the first projection and then try to prove that. Think about the conceptual difficulty you would face when doing this in the unconstrained world compared to the constrained world. In the unconstrained world, you went as far as you wanted. There's no limit. Here, every time you're projecting it back. So each time, you possibly will not get everything you want because of where you are with respect to the constraint. Okay, how much will you change? Surprisingly, we still get T. But do something in addition only in the numerator. So that is what we will try to prove. So the rate of convergence will not change, unconstrained or constrained. It's only the numerator, so the additive term will be larger. In terms of the T, it will remain the same, which is rather surprising. But good to remember this, that constrained or unconstrained gradient descent or projected gradient descent, as long as things are beta smooth, gives you linear convergence. See, then we didn't assume beta smoothness, we just got 1 by square root t, which is much weaker than 1 by t. Now we are attempting 1 by t. And the key ingredient we really used to prove this lemma was the following. Okay. Let me say. So lemma We'll write lemma 1 and lemma 2. So when f is convex and beta smooth, what we showed was in the unconstrained world, which happens to be true even in the constrained world. So f of x minus f of y minus gradient of f of y transpose x minus y is less than or equal to beta by 2 x minus y. This was shown in the class. Okay. And this is true even when x and y have to be constrained. And corollary to this, really what we used to prove that result was the following, that in one step of the gradient, this is where we don't get what we want. So what is the one step of the gradient? So, and we took the step size to be equal to 1 by beta del f of x. If you apply this with x equal to x minus 1 by beta gradient f of x and y is equal to x. Just apply this lemma by setting x is equal to x minus 1 by beta gradient and y equal to x. What will you get? This is the first term minus f of x. There will be lots of cancellations, and what you will end up getting is minus 1 by 2 beta gradient of x. And this was nothing but one step of the gradient descent. You don't get this when you're doing projected gradient descent. That's where the problem is. Otherwise, the proof would be identical. So this is not my one step in projected gradient descent. There is an in-between projection step involved, and that I can extract. So this is still true. We use this as our workhorse. We won't have this inequality. So you have to do a workaround. We want something like this. In each step, some improvement is what we want. We won't get it directly from here. So this was shown in the class already. This was a corollary. And it worked because this was nothing but the gradient descent with eta equal to 1 by beta. So we want something like this, but we won't get it from here. We'll find other ways to do this. All right? Is the idea clear why you can't get something like this? This is just the equation wise that this is not a gradient step. But think of conceptually. Your gradient wants you to push and get that much improvement. But the constraint is going to put you back into the constraint set. So there is no reason. So this particular thing, let's say, if the sky was absent, you are at some particular point and it took you somewhere outside. And that guaranteed that so much improvement was made. But your algorithm is going to push you back here. Now you can't guarantee how much improvement you already made. So we'll have to come up with something else here, which is what will give us the result. So directly you can't use that inequality. But still not too difficult. So remember lemma 1, keep repeatedly using it. So let's call this lemma number 3. Let x comma y belong to the constraint set. Let x plus be the projection of x minus 1 by beta gradient of x. Okay. So think of this as the initial point, gradient direction, and then projecting it back. And let h of x is equal to beta times x minus x plus. Then the following holds true. f of x plus minus f of x, so f of y is less than equal to h of x transpose x minus y minus 1 by 2 beta h of x. So this needs to be compared with our lemma number 2, which is no longer really what we would have asked for. Write it and tell you what is the, so this is the corresponding result we will get for the constraint case and we'll use it. For the unconstrained world, I showed you some result, which was so as I said, this is what I wanted. I don't get it. So this is the counterpart. This is the best I can get. And from here, the proof will not be too difficult. So we'll first prove this and then we'll prove the actual result after writing the guarantee. We're not even written the guarantee for the algorithm just yet. Okay, so why do you think this is okay? What is going on? It's saying, look at the projection. Compared to any arbitrary y, this function x minus x plus multiplied by x minus y and the norm of h of x itself. So let's pictures might be interesting. So take any x and y. So x is here. X minus, let's take it outside. X minus 1 by beta del f. Just for illustration, let this be x plus. What it's saying? That f of x plus minus f of y. So suppose the function was of this type. This is the valuation of f of x plus minus f of y. What is this less than equal to? X minus, so this vector, x minus x plus, that's the vector which is used to define h of x. So h of x transpose is nothing but x minus times this vector. There is something of an inner product between this one and this one. So suppose this minus this quantity, which is nothing but the square norm of this. That's what this lemma is trying to tell you. And beta is just thrown in because of the definition of h of x. Otherwise, everywhere what we're going to do is take the step size equal to 1 by beta. That's what essentially it will mean eventually. But for the moment, beta is anything arbitrary. So that's what we want to show. So geometrically, that's what is going on. All right. Okay. So how should we proceed to prove something like this? Use the projection lemma, which we wrote down first. Projection of y minus y times projection of y minus x y less than equal to 0. So we use that to begin in some sense. See, x minus 1 by beta gradient of f of x can essentially be outside. And that projection is x plus. So we can actually readily apply the projection lemma to begin. What would that give us? If I apply the projection lemma, so y should really be thought of as x minus 1 by beta gradient of f of x. That's the only quantity which is lying outside of x. Sorry, the feasible set chi. Oh, so see, I'm going to, here I've taken y to belong to chi. So this should really be, let's call it that. That is the only quantity which is lying outside. Okay. From I'm calling it the projection lemma. What can you tell me? is just verify this is fine. X minus Z times X plus minus Y will be less than equal to 0. What is X plus? Projection of Z. So projection of Z minus Z multiplied with projection of Z minus Y, which is lying inside the carry. So this better be less than equal to. So just reinterpret this. I'm claiming that this is equal to, essentially, if I just write Z to be that quantity, I'll get del fx transpose X plus minus Y less than equal to H of X, X plus minus Y. Just using the definition, nothing else. If not, somebody doesn't see it, let me know. That is why beta has been absorbed in H of X. Here, beta will pop out, which will be absorbed in the definition of H of X.
How do we get f of x?
F of X star. Here, the claim has no X stars.
If x plus, like,
How will we get this? So far, we have not even touched F of X plus. Is this okay? Is the question. You're running too far ahead of me. For the moment, I'm not saying anything. From the projection lemma, this is clear. All I'm doing is pure algebra. There's nothing here which is of there's nothing non-trivial here. I'm just putting the value of Z over here and using the definition of H of X. That's all. Nothing else. Is everybody happy with this? Checked. All right. So I have this. Now what should I try to? How should I proceed towards working towards my goal? What do I want to care about? F of X plus minus F of Y. That's what I want to control. And as I said, this lemma is still true. This is not violated. Okay. So this tells you something about F of X minus F of Y minus the gradient of F of Y times X minus Y to be less than some norm distance. So this lemma is still true. So you can use that if you want. So let's call this equation number 1. Okay. So what do I want to control? I want to control F of X plus minus F of Y. What should I add, subtract? If I wanted to add, subtract something here, what would be the natural quantity? X star. I have no, see, in this lemma, there is no concept of minimizing of nothing. Look at the lemma. It says nothing about optimizing. All it has is a point, a gradient step, a projection. That is all it has. X and X prime. X prime. No, the natural candidate should be X, right? From X, I am doing something. So let's add and subtract F of X from this. All right. Now what should I do? Which terms should be combined? Which term should be kept as it is? From the lemma, which I just cited, what can I bound this by? This lemma can be applied there. For the first two terms, I'm going to apply that lemma to get less than equal to gradient F of X times X plus minus an X and plus beta over 2 X plus minus X whole square. Just purely applying that lemma. And what can I say about these two terms? Just by convexity?
This equals to
X minus Y. Yeah. Just purely convexity. and this is from 1. All right. Now what should I do? What can I do? What's interesting?
Use the triangle inequality of x minus y. So that we can get a term of x term.
Okay, keep going. So this should be not x, y, x. So something cancels here, if you have noticed. There's a minus x and there's a plus x. So this goes away and this goes away to get me gradient of f transpose x, x plus minus y plus beta over 2 x plus minus x. I recall the definition of h of x was simply beta times plus minus x or x minus x plus. It will not matter here because it's a square. It was x minus, so let's put a minus here. So this is also equal to del f transpose x, x plus minus y plus 1 by 2 beta h of x square. Something I want, right? In my lemma, I want something of this type. But this is a negative sign. I currently have only a positive sign. All right? Now what should we do? Look at what I want. I want h transpose x times x minus y minus 1 by 2 beta. What I've accomplished is I've got h of x square. I've not got a negative sign. I've not got the first term. So what do you think I should do to get rid of the gradient? Instead of gradient, I want h to somehow sit there.
Can we read the last slide?
Sorry?
In the last lemma, like
Which lemma?
in the unconstant case.
I've been naming them.
In the unconstant case, when we get this proof,
Mm-hmm.
we definitely use that.
This was the key step, these two. That's why I recalled both of them.
No, we use that fact that del of x star is 0, and we use the lemma.
Yeah, that was true because of the unconstrained nature.
Yes.
Yes.
But in the constant.
I've not used it anywhere, right? Because I'm not proving anything with respect to the optimization. For the moment, all I'm interested in is proving this lemma. So how do I, okay, so where should I be? So I want h to appear here rather than the gradient of f. How do you think I should do that?
Then less than or equal to h transpose.
That's what we proved in the last board. So from our projection lemma, what did we prove? Keep track of what all we are doing. What is my equation number 1? It's exactly that. The gradient f of x times x plus minus y is exactly less than or equal to h transpose x plus minus y. That's precisely what I want here. So h transpose x times mistake by 2 beta. Okay, so now final step I will leave to you to figure out. I want to get rid of x plus here and I want to move from plus to minus. What is my definition of h of x? Is this. Can you tell me how to do that? Objective clear, right? I want to get rid of x plus. I want to get rid of the plus sign on 1 by 2 beta.
With h of x by minus b.
Okay. That all? Let everybody see it. This is the definition of h of x. That's all. And don't touch the last term, touch the first term. What is h of x multiplied by x plus minus x?
You just add a X and subtract it.
Mhm.
Then use the rest.
Okay. Let's see. What do you want me to add? H transpose x multiplied by x plus minus x. Is that what you want me to write? And plus h transpose x, x minus y. That would be correct. Yeah, okay. This is as it is. Then what do I get? That is beta, right? Something more than that. If I multiply,
Yeah, beta times H of X.
okay, but so what are you claiming this is equal to? See, you have a hint right here. It better be 1 by beta.
There will be 1 minus.
It better be 1 by beta because I want
So there will
with
be
a minus sign. So this is the way I've written here, it is minus beta times x plus minus. So this is in fact true, and this should be minus 1 by beta. Sorry, should have this. Now the first term is nothing but minus 1 by beta mod h of x plus this is as it is plus 1 by 2 beta h of x. You add this and you get your result. All right. So we got to the lemma. Now, what do I want to use, or how should I use that lemma? So this is the lemma we proved for ourselves. We want to control essentially in one step. So let's say f of xs minus f of x star is what we really want to control. How do you think we can approach this? Or you can think of it in one step, how much improvement I'm making. That's also good enough. So f of x plus 1 minus f of xs. So if I plant x plus s xs plus 1, it is nothing but exactly this. So what is happening in the algorithm? You're at xs. How do you go to xs plus 1? By essentially taking the projection of xs minus 1 by beta gradient of f of xs comma x. That's exactly what xs plus 1 is. So what fits the bill in here? So if I want x plus to be x of s plus 1, y to be x of s. One step, how much improvement I'm making? How much will this quantity be if I do that? The right hand side.
X
So this is-
x minus x star will be basically the one we get gradient of x.
How much will this be? In our definition, this is xs plus 1. This is exactly x of s. That's the projection I'm making, right?
Yes.
So y is nothing but x of s. X is also x of s. So this whole term actually is 0, and all I get is a negative quantity. That's one thing I would like to get from this lemma. What more can I get? So this will give me a control over consecutively how much improvement I'm making. It's clear to everybody. This in between definition was created so that x turns out to be x of s, and x plus turns out to be x of s plus 1, and y is any arbitrary point. So I can always evaluate it as y equal to x of s. What more can I get? Now compared to this, the function distance from x star. Here I got one step. I'll do everything. Just trying to say this before I do it. If I take it as x of s and this is x star, what can I say? In terms of distance, in terms of compared to the optimal point itself. In one step, we know it is at most this quantity. But in compared to the distance to the optimal, what will be the bound on the right hand side? This is anyway negative. I can throw this away. How much is this quantity? Is simply by Cauchy-Schwarz norm of this times norm of this. And that will be sufficient for me. Two things I want to extract from this lemma. One, in consecutive steps, how much improvement I'm making in terms of f, and in sth step or tth step, how far I am from x star. Both I can extract. Something is not clear? So what is algorithm? Algorithm is the same. It's written there. Algorithm is projected gradient descent. All the change I made, descent, is eta is equal to 1 by beta, where beta is a smoothness parameter. Early on, we were choosing eta to be 1 by square root t, something to do with the end, the diameter as well as the Lipschitz constant. Now we have removed the dependence on t. Now it is just simply 1 by beta. Right? And that's why this lemma becomes applicable. So applying the lemma, did I name it 3? Fully? It is 3. Very good. First I get f of xs plus 1 minus f of xs to be at most minus how much? 1 by 2 beta gradient, sorry, not gradient. H of this quantity, h of xs. That's, and one more time. F of xs plus 1 minus f of x star to be less than equal to, again, norm of h of xs times norm of xs minus x star, dropping the negative quantity. Both are okay? Okay, so we did something like this last time. We defined delta s to be f of xs minus f of x star, right? And then we wrote a recursion in terms of delta s. So delta s plus 1 is equal to something something as a function of delta s. What can I do here? So that was our trick to eventually prove that 1 by t minus 1 bound. We wrote down the recursion as a function of deltas. But we needed something in between to hold. What is that something in between? So how do I ensure that delta s is actually decreasing? Can I do that?
Okay, add and subtract factors, then you get.
So in the first, in the second equation.
Yeah.
Like f of x plus 1 minus f of x is x. If we just have a subtract f of x star here, we'll have delta s plus 1 minus delta s less equals to 0.
Okay.
And that is true for all s.
Yeah.
So we'll get delta s is decreasing.
Convince me. Why is that true?
Delta s plus 1 minus delta s is equal to f of x s plus 1 minus alpha.
Yes.
And that is so negative.
Correct.
So delta s plus 1 minus delta s is that.
Right. So that is straightforward. Look at these two equations and try to understand what is necessary for me to get what I want essentially. I want to write recursion. And to solve that recursion, I would need a technical condition. What is the technical condition? Just there is nothing outside of this board. Everything is written on the board. The second equation is the right hand side, which is a function of the distance from the optimizer, not the function distance, the distance, xs minus x norm. If I don't establish that that is non-increasing, can you get what you want? That's a necessary feature, I claim. That if the distance from x star is increasing in each step, you should not expect anything to happen. Because then what is the left hand side? The distance from x star in terms of f of x s plus 1 minus f of x star. And if this xs minus x star seems to increase, the distance also will keep increasing. The bound will not be sufficiently good. So you need to establish that x of s minus x star, the distance, better be decreasing or non-increasing. How do you establish that? Once you have that, then you are in business. Then you can do everything you want.
We are in a bounded case, right?
Yes.
Right now. So that x is minus.
That's not good enough. If you just bound it by b, it won't be good enough.
That means you really want that it is still decreasing.
Non-increasing. Non-increasing is okay. Because non-increasing tells you something.
That's why the t will not be sufficient.
Upper bound. So how do I know it's not increasing? B is only an upper bound on the distance. So in each iteration, possibly you're increasing it. You have that algorithm which is moving away from x star. Initially it was 0. The algorithm kept moving towards the boundary. You should never expect an algorithm of that type to have a guarantee of 1 by t, right? It should not go anywhere. What are we at the end of the world? We are not saying anything. So I'm not written at the guarantee which you are going to get. This will be independent of the diameter. Yeah. To be sure. With the proof. Yeah, this will be some term with see, even in here it mattered. Even in the unconstrained world, the guarantee depended on the distance from the starting point. But that's just one fixed term. And then you get divided by t minus 1. So the more you progress, you're going to shrink it. Similarly, we're going to get something of this type. But you should really see that this is not, if suppose the algorithm which is increasing, you should not assume, you should not expect that algorithm to converge anywhere. But the distance to the, unless the function is some very weird function which is constant. We're proving for every f, you're not proving for some special f's. So this better be non-increasing. And once you establish that, then you write in the recursion and get everything. So how do you establish that this quantity is in fact non? So somehow you want to show that this is less than equal to x of s minus 1 minus x star. Once you do that, these two inequalities are enough. So what is xs in terms of x of s minus 1?
Projection of
Yeah.
projection of x is minus 1 by beta del f of x is minus 1.
Okay. Will that help me somehow?
If you blindly put the value of x's, then somehow we have to argue that involved in a prediction.
What is the relationship between xs and x plus minus 1 which I can exploit? We have all the definitions of the world sitting in front of us.
Excited the projection.
What is my definition of h of x?
Which beta x
Then just change it here. That's correct. What was x plus? X plus was nothing but the projection. So how can I write this as the left hand side? Can I write it as xs minus 1 minus 1 by beta h of xs minus 1 minus x star? Let's take this quantity here. Is that correct? What is x plus? X plus was the projection. So it's sitting inside there. Beta gets cancelled. X gets cancelled. It's nothing but exactly x of s. And once you see something like this, how do we open? I want something, the distance between this and this, right? That's what I want. So this is equal to x of s minus 1 minus x star, the whole square. We've done this trick many times over. 2 by beta h of xs minus 1 times xs minus 1 minus x star and plus xs minus 1 minus x star. Am I doing the whole thing correctly? No. All I get is just simply h of x. 1 by beta square h of x square. So this term I want. What about this plus this? We actually said something about this very interesting. These two terms. Look at my lemma here. This lemma, the right hand side is exactly what I have currently. What is this compared to what I want to use? What are these things? There is an x star here and xs minus 1. What do we know about f of xs minus 1 and f of x star? By definition, x of s minus 1 is an inferior solution. So f of x minus 1, f of x of s minus 1 is greater than equal to f of x star. So you just use that inequality by playing with x of s minus 1 and x star. So this is as it is. So this is going to be x of s minus 1 minus x star. And using lemma 3, you essentially get minus 2 by beta is as it is. This is less than equal to 1 by 2 beta this should be x of s minus 1 everywhere. Plus 1 by beta square h of x. This and this cancels off. You end up getting just the first. So this is from lemma number 3. By noting that f of xs minus 1 is greater than equal to f star. You want me to revisit that? I'm happy to do that. So what do we have? Let's just look at this being x of s minus 1 and this being x star. What is this quantity? Greater than equal to 0. So all I do is put a 0 here and forget that this even exists. Now I have h transpose x, x minus. So what is this x? X is x minus 1. This is x star plus minus 1 by 2 beta h of x star. That's exactly what I have. So all I use the fact is x of s minus 1 is an inferior solution. Okay. So now I've established that x of s minus x star is a non-increasing sequence. Now I can write delta s as before to be f of xs minus f of x star. And what you end up getting is this. I will just write so that I can finish on time. Del s minus 1 minus 1 by 2 beta x1 minus x star del s square. This is easy just by what we have got so far. These two things which we already shown, this directly give us this quantity, and you solve it for delta of, how much is that? Delta s is less than equal to 3 beta x1 minus x star the whole square. I will indicate what extra do we get. This is the extra term we get compared to the unconstrained case divided by s. So we got, instead of 2, we got a 3, and this is the extra compared to the unconstrained case. But surprisingly, or rather thankfully, the denominator is the same. So it's still linear convergence. So even in the constrained case, projected gradient descent with 1 by beta step size gets you linear convergence. Any bit hurried up, this is easy. And from here it again is directly follows as long as xs minus x star is non-increasing. The difficult part is to establish that. And the main workhorse really is this particular lemma. If one has to pay attention to, this is the lemma to pay attention to. This works when we are working with the constraint space. All right, let's stop here.